Hello guys, welcome back to class. In the previous sessions, we have seen binary search trees, BSTs, right? Various how to construct the binary search tree, how to insert, how to delete, how to search in the BST, right? And how to find min, max, seal, floor, right? How to check whether the tree is BST or not. Various operations we have done, and we understand how to work with BSTs. Now, from those, I'll ask you quick questions. What is the time complexity of various BST operations? What's the time complexity of various binary search tree operations? So if you take a search operation or insert operation or delete operation, what's the time complexity? I remember the time complexity with the BST. For most of the operations, almost for all the operations, the time complexity is yes, because time complexity is H or N. It is almost big O of H, right? We're calling it as height, or this H is important for us. So H can be so you call it as big O of H. So H can be a log n or H can be n. In some cases, H can be n. In some cases, H can be log n. N or log n, right? So which is the better for us? If you replace H value, so H can be either n or log n. It means your time complexity goes big O of log n or big O of n. Which is the better for us? So what we have to maintain always? What we have to maintain always? We need to go for log n only. So that is the main goal for us. But is it possible always to maintain log n? We'll just have a look. I'll take some binary search tree. So this is my BST. Say 50 is a root and 30 here, 60 here, and I have 70, this side 55, and here 35, and say 20. So this is my BST. In this, what is the N? What is the N in this? N represents number of elements, right? N represents number of elements. We have 7 elements. Okay. What is the height of this? Height you calculate as this is the 1, 2, and 3. Height is 3. Height is 3. So here H3, this we can also call it as, can I say it as log n, right? Because not n. So in this tree, if you are searching, suppose I am searching for 55, for example. When I am searching for 55, how many searches you will do? Start with the root. You are searching for 55. 55 is greater. 55 is greater. So come to the right side. Again, you have a 60, but I am searching for 55, which is smaller. Come this side. So how many searches you have done? How many comparisons you have done? Just 3 times. Just 3 times. That's what your height. If this is the case, wonderful. If this is the case, now height is 3. So my time complexity for a search operation is big O of H, or I can say big O of log n. In this case, even for insert also similar will come. Maybe it may be height plus 1 sometimes, height plus 1 sometimes. Overall log n. But But you take another binary search tree. You take another binary search tree. 10, 20, 30, 40, 50, 60, and 70. Same elements only. So if you see exactly similar elements, I inserted exactly similar elements. Or if you want, instead of 40, I use a 35 here. Maybe make it as 35. 50 is 60 is there. 70 and 55 also we have. Okay. 10, 20. Instead of 10, we have something. Yeah. So in the second case, guys, what is the n? How many elements we have? Roughly 7 elements we have in this also. And what is the height of these guys? Height is 7. So this is the case where your height is n. Height is n. So in this case, what's the time complexity for such? Time complexity, you have to say big O of h. It means it is big O of n only. Big O of n only. Big O of n only. You search for and take a simple case. I want to search for a key called 70 here. Here I have seen, suppose I want to search for a key 70 in this case. First case you take 70, I want to search. Then it has taken 3 iterations. Here I want to search for a key 70. So first take 10 I was searching for 70. 70 is greater, so right side. 20. 70 is only greater, again right side. Third, fourth, fifth, sixth. Finally, you're taking 7 comparisons. 7 times you are doing it. So the time complexity is big O of n. Is this acceptable? Is this acceptable for BSTs? If you are taking big O of n, then why have to come for binary search trees, guys? I have better things. So if I do, for example, searching in arrays only, it will take, I think, less time for me. I have a linked list otherwise. We have other data structures. But with n case, we no need to come for binary search trees, right? So what is the problem now? Tell me. So what we want to do is, I want to maintain height of the binary search tree as log n, not the. So from these two diagrams, here height equals to log n. In this case, height equals to n. Height equals to log n in the first case, and height equals to n in the second case. But I don't want to maintain height equals to n. I want to maintain height equals to log n. Because of maintaining height equals to log n, I can do my search operation BST fastly. I can do insert delete operations also very, very fastly. So what to do is clear, right? So I want a BST something like this. But this is also a BST only. But I don't want a BST something like this. So what I have to do now? What I have to do is, you have to make the balance in the binary search tree. You have to make the, so what we are thinking now, you make self-balancing BST. Self-balancing, balance the binary tree. Yes, balance the BST. What is the goal of balancing? What is the goal of balancing, guys? Just now we discussed. What is the goal of balancing a binary search tree? Is to keep the height, as log n, to maintain the, yeah, time complexity is automatically comes. We have to think about height. If you can maintain the height as log n, if you are maintaining the height as log n, then automatically time complexity will be the log n. So our goal is to maintain the less height, not the more height. So how you will balance it? How you will balance it? You can balance the Banach history just by you rearrange the nodes to balance the BST. You rearrange the nodes to balance the BST. That is to maintain the log n height. This process of rearranging is called as rotations. Here, this process of rearranging is called as rearranging process is called as rotations. Binary history rotations. So what is our goal now? Whenever you write a BST, you have to maintain a log n height. To maintain the log n height, you need to do some rearranging of the tree automatically. So the rearranging process we are calling as rotations. So you need to rotate the binary history. Whenever you do the rotations, automatically it will go. I'll just tell you one small case. Take one simple example. I have a keys like this. I have a keys are 10, 20, and 30. These are my three keys. So first insert 10, first node. First node means no problem. Yeah, insert. Then insert 20. So where 20 will come? 20 is the greater than 10. So it comes the right side. I think up to this is fine, right? Up to this is fine. Next, go for insert 30. 30 is again greater than 20. It comes the right side. So you tell me, is this a balanced? Is this a balanced, guys? Is this a balanced binary history? This is not a balanced BST. So how you can make balanced? You have to make this as a balance, means you do rotations. So the rotations you do, I'll explore about the rotations more clearly later in the session. You do this kind of rotation. You do the rotation towards the left side. When you do the rotation towards the left side, so it becomes here after rotation, so your 20 becomes the root. Rotation means like this, you are moving. Move this. And 20 child, 30 is the rastis. And 10 becomes the child of this. Is this balanced, guys? Second one after rotation. So rotation is done. So this is a balanced one. This is a balanced. This is a balanced one. This is not a balanced. So here we have three elements, but height is 2. Yes, there's a minimum we can make. We can't do more than that. So like this, there are multiple types of rotations. We'll talk about the rotations later. So if you can do the rotations, then your binary history becomes balanced. Whenever binary history becomes balanced, then height remains minimum. Whenever height remains minimum, the time complexity becomes your height, which is log n. That is a key goal of this entire process, right? No. So you understand self-balanced binary histories. Is that clear, guys? So whenever you're constructing a binary history, you do the rotations on the BST whenever it is becoming unbalanced. whenever it is becoming unbalanced. For example, now you take, suppose this is the tree I have. Initially I have a 10, 20. Up to that, cool. But whenever I am inserting 30, it is becoming unbalanced. Then I am doing rotation. So whenever your tree becoming unbalanced, immediately do the rotation. When you do rotation, it becomes balanced. So you're maintaining the height. Clear, guys? So this self-balanced Banach's tree. Is this clear? Any doubts on this? Now, types of self-balanced BSTs. There are multiple types are there. There are multiple types are there. There are multiple types are there. In that, most important, I'm going to explore. One is the AVL trees, and second is red black trees. Splay trees, etc., are there, but these two are the most important and most powerful, right? So question from Vikas is how to check whether the tree is unbalanced. Very good. The question is very important. Yes, take this question as how to check whether BST is balanced or unbalanced. Is that the question? Because this is depending on the type of self-balanced BSTs. In AVL tree, the way of checking is different. In red-black tree, the way of checking is different. So self-balanced BST. The actual implementations are AVL trees. AVL tree is a self-balanced BST. Red-black tree is a self-balanced BST. So when you are implementing self-balanced BSTs, you are implementing either AVL tree or red-black tree. So the way how to check BST is self-balanced or not is different in the AVL tree and different in the red-black tree. So that this question, Bikash will answer it in the AVL tree, and 2 times I'll answer. How to check in the AVL tree, how to check in the red-black trees. Now, so I think at the beginning we have seen a beginning of the binary search trees, BSTs. So in Java, all of you are Java developers. We are learning data structures algorithms in Java. So in Java, whether BSTs are implemented anywhere in Java, whether BSTs are implemented anywhere in any collection API, where which is Java collection API using the BSTs. Pankaj, hash map and hash set are using hashing technique. Hash map and hash set are using hashing technique. Tree set and tree map. Yes, Mona and Bikash. Tree set and tree map. And BSTs means when you are going for a BSTs, you have to choose either AVL trees or red-black trees. Mainly in Java, remember guys, Java tree set and tree map, Java tree set and tree map are implemented based on red-black trees. Java tree set and tree map are implemented based on self-balanced binary search trees called red-black trees. Clear? AVL trees also not used. AVL trees are more strict than red black trees. That's what they didn't use. Red black trees are the best mostly when you say that. Anyway, we'll explore it. So up to this clear. Now we will study the AVL trees fully and red black trees fully. Can I go to AVL trees, guys? Okay, let's start with AVL trees. What is AVL tree? AVL tree is, it is a BST. It is a BST. It is a Banach's tree. AVL tree is a Banach's tree. So Banach's tree rules, you know, right? What are the rules of Banach's tree? What are the rules of Banach's tree, guys? Left side lower and right side higher than root. Left side lower and right side higher than root. That is the basic funda you follow because it is a BST ban. Second very important is AVL tree is a self-balanced. It's a self-balanced. Because of self-balanced, what is the advantage you're getting? Can you tell, please? What is the advantage of balancing the BST, guys? What is the advantage of balancing the BST? Just to minimize the height. Wonderful. This is to minimize the height and to keep the height as log n. Simply, otherwise you can say to keep the height as log n. So BST, it is a BST, it is self-balanced. Or you can say in one line, AVL tree is a self-balanced BST. AVL tree is a self-balanced BST. Okay. Now, in AVL tree, how it will balance? How it will balance the Banach's tree? Or the Vikash has asked the question previously. How to check it is going for unbalanced? How it is balanced? How to check whether it is balanced or unbalanced, right? So if you know the mechanism how to check balanced and unbalanced, you can understand by seeing this, oh, this is going for unbalanced, I have to balance it like that. So this is depending on height factor, HEIGST, height factor, depending on height factor. This is also called as, otherwise you can call this as balance factor. It will use a number called balance factor. Balance factor equals to, always you have to calculate the balance factor. This is left subtree height minus right subtree height. Just you find the left subtree height minus right subtree height. So you calculate the left subtree height, calculate right subtree, left height, or you shortly call it as LH, left height, minus RH, right height. So this number always should be less than or equals to -1 or a 0 or a 1. So the difference balance factor should be a -1 or a 0 or 1. -1 or 0 or 1. Or if you find a modulo of this, so you can take it as absolute value. Means if you avoid the negative values, balance factor is LH minus RH. I am taking the absolute number. This should be less than or equals to 1 only always. So balance factor is clear, guys. We'll do an example. Then you can understand. So take the first example. So I have 25 and this side 20, some value, some input data. This is my 35 and I have to maintain a BST. It is a BST, guys. BST rules has to be followed. And this is a 10. Okay. So now you find out the balance factor for every node. Find out the balance factor for every node. This is important. Understand carefully. If you understand this, this is the whole story of AVL trees is depending on this only. So first take the node 10, guys. For node 10, what is the balance factor? Tell me. Node 10, what is the balance factor? Right subtree height minus, left subtree height minus right subtree height. So for 10, what is the height of left subtree for 10? For it is not there. So 0, right? So this is 0 minus, right also 0 only. 0 minus 0 equals to 0. Okay. For 30, 30 also 0 minus 0 equals to 0. Or you can remember another thumb rule that for a leaf nodes, always balance factor is 0. Can I consider leaf node 0 only always? Yeah, leaf node 0. Now calculate 20, guys. 20 means what is the left height? For 20, left one height is there. Right 0. Can I call this as 1 minus 0 equals to 1? 1 minus 0 equals to 1. And take 35. 35 means 35 we have a left one. 35 we have a left one. Otherwise, I want to take a negative. To take the negative, I'll change this to 35 and I'll take this side as 40, for example. 40 anyway 0. This is 0 minus 0 equals to 0. And for 35, tell me. 35 left is 0. 35 left is 0. Right as 1. 0 minus 1 is 0 minus 1 equals to minus 1. But when you consider minus 1, okay. 0, okay. 1, okay. It should be between that. Or if you take a positive values, minus 1 you take as absolute of minus 1 as a 1. So it should be less than or equals to 1. Less than or equals to 1. So take now tell me the balance factor of 25, guys. 25. Balance factor 25. 25 is 0. For 25, left subtree is height is 2. This is 1, 2. Height is 2. This side 1, 2. So this is 2 minus 2 equals to 0. So tell me, is this AVL tree? Is this AVL tree, guys? Yes, this is an AVL tree. Because how can I say it is self-balanced? I'm finding self-balanced because of balance factor. Point is clear, guys? Okay, we'll go for another example. I'm taking 25, 20, and 10. For 10, balance factor always 0 minus 0 equals to 0. 20, 20, guys, 1 minus 0 equals to 1. 25, you tell me. 25, you have to tell. 25 balance factor, guys. It is left side 1, 2. 2 minus 0 equals to 2. So tell me whether it is AVL tree. This is not an AVL tree. This is not a AVL. This is AVL tree. Let's take another example. I have a 10 here on top, then 20, then 30, then 40. So this is 0, this is minus 1, this is minus 2, this is minus 3. The minuses when you make absolute, this is not at all, this is not a. But remember, don't go for minus 3. Don't go for a 3 balancing factor. So whenever your BST becomes unbalanced, whenever a BST becomes unbalanced, do the rotation immediately. Do the rotation immediately. What is the meaning of that? First, you are inserting 0, guys. I'll take another case. Come here. Yes. The point here is whenever BST becomes unbalanced, then do the rotations immediately. Don't wait for bigger. Okay, what it means? First, I am inserting 10, guys. Insert 10. So as of now, whenever I insert elements, then you check the balance factor. What's the balance factor of this? As of now, balance factor is 0, single node. Fine. Next, I'm inserting 20, guys. Okay. Now check the balance factor. Tell me balance factor will be updated, right? The tree balance factor has to be updated. You update the balance factor. Now this is 0, guys. This becomes 1. 10 balance factor becomes 1. As of now, it is balanced or not? As of now, it's balanced or not? As of now, it is balanced or not, guys? Yeah, -1 or 1. Okay, Balmiki. Chalta, right? -1 or 1. Okay. So as of now, it's balanced. Okay. Next, I am inserting 30. Whenever you insert a node, immediately update the balance factor. This is 0, this is 1 or -1, whatever. And now this is 2 or -2. Now, which element is causing the unbalancing, guys? Which element insertion is causing the unbalancing? Which element insertion? Dina, no. When I insert 10, I think it is okay, right? 30. Now, just now when I insert 30, it has becoming unbalanced, right? 30 is causing unbalanced. And which node is unbalanced now? Which node is unbalanced? Whose balance factor is greater than 2? 10 is, this is unbalanced. This is becoming unbalanced. This is causing the unbalance. Then you do the rotation. Where you inserted this? Where you inserted this node 30? 30 is causing unbalanced. Where you inserted 30? Right side, right? This is the node which is becoming unbalanced. From this, you take right side. So where you inserted? Right. You inserted right. This rotation is called as right rotation. Immediately, okay, these rotations we'll talk later. Don't see this now. Understand? Immediately you do this. So this rotation you do, then this becomes 20 here, 10 becomes here, 30 becomes here. When you do the rotation, what is the before rotation? What are the? This is a 2 actually. This is a 1 actually. This is 0 actually. This is the balance factors before rotation. That's what 2 is there. We are rotating. After rotating, you again update the balance factors. So this is 0 only, correct? This becomes 0 only. This also becomes 0. Now, wonderful. This is a fully balanced. After the rotation, this is before rotation unbalanced. After rotation, it is balanced. So height is minimized. We are happy with this height. Is this clear, guys? AVL tree introduction is clear. So we understand AVL trees are self-balanced binary system trees, and we are deciding whether it is balanced or not depending on the balance factor. How you are calculating a balance factor? We are calculating balance factor by calculating a left subtree height minus right subtree height. You take the absolute value of that, so it becomes absolute value means you will take only positives. You avoid the negative. So left height minus right height should be less than or equals to 1 only. Okay, or if you take the values wise, either -1 okay, 0 okay, 1 okay. These three are accepted. If 2 comes or -2 comes, then it becomes unbalanced. Immediately do the rotation. Okay. Munna, it is telling a left rotation. Yes. When it is RR, you do left rotation. That will go back to the next. We'll go to the rotations only. So is this clear, guys? AVL trees introduction part is clear. Okay. So we'll go to the rotations now. Yes, we'll understand rotations now. Come back here, guys. Rotations. Almost whatever the size of BST you take, your BST can have 100 elements, 200 elements, 300 elements, or 1,000 elements, no matter the height. Rotations always will happen on 3 nodes only. It will impact 3 nodes only. It will impact only 3 nodes. Even when you have 100 nodes, when you're balancing by doing a rotation, it impact 3 nodes only. So why I'm telling 3 nodes only will be impacted when I have 100 nodes, that you'll see now practically. So I'll take a simple case, multiple keys. The first case I'm taking here, guys. You see how to do that. Suppose I have a keys here, girl. 10, 20, 30. So construct the tree. Based on this, construct the tree. So first you insert, guys. 10 I am inserting. Wonderful. Up to this, it is balanced. Next, insert 20. 20 comes right side here. I think up to this also balanced. Next, insert 30. Now it becomes unbalanced. Right? So we have to rotate this. How to do that? We'll see. What is the height of this now? What's the height of this? 3. This is not accepted. Right? Next, go to another case. Second case, keys equals to, so you take it as 30, 20 and 10. Reverse I am taking. Now first insert 30. Okay. Then 20 less than means it comes right side. Up to this balanced. Whenever I insert a third, then it is becoming unbalanced. So here also height is 3. So this I don't want, because 3 elements, 3 height means not acceptable, right? Okay. Next, third case, you take 10, 30 and 20. 10, 30 and 20. These are my keys. Okay. First insert 10, guys. Insert 10. Next 30, bigger, this right side. Then insert 20. 20 is lesser. What's the height of this now? Tell me the height. Is this 3 only height? Height is 3 only, right, guys? Height is 3 means not acceptable. 3 elements and 3 not acceptable. Next, another set of key I'm taking. 30, 10 and 20. 30, 10 and 20. I am playing with the 3 elements. 3 elements, you have 6 combinations. Now, first 30, then 10 you have less than this. Next inside 20. 20 is greater than 10. It comes this side. Now, height here also 3. Height here also 3. These are 4 combinations we have. Next 2 you see, very important. Keys are 20, 10, 30. Fifth one, 20, 30 and 10. Okay, do for this. First insert 20, guys. Okay. Then 10, less than that. Okay, here. Next 30, greater than 20, here. So balance it, right? Balance it or not? Next, first insert 20. Okay, done. Next inside 30, 30 greater, so right side here. Next 10, 10 means less than 20 here. So both came same only, right? This is also acceptable, guys. Height is okay. This is wonderful and wonderful. Fine. So first case not okay because tell me the balance factor of this, guys. This is 0, this is -1, this is -2. That's what not acceptable. This is 0, 1 and 2, not acceptable. This is 0 and this is 1, this is 2, 2 or -2, whatever, or -2 here. This is 0, this is 1 and this is 2. In any case, the last element is causing, so this is not okay, this is not okay. One, height is more. In general, you can understand it is becoming unbalanced means whenever the number of elements equivalent to the height, definitely you can say, oh, it is unbalanced. Or in the case of AVL tree, how can I say it is unbalanced? In the case of AVL tree, guys, how can I say it is unbalanced? Whenever the balance factor becomes 2, immediately 2 or -2, 0 accepted, 1 accepted, -1 accepted. Whenever balance factor becomes 2 or -2, immediately you say it is unbalanced. And you have to convert first 4 cases, this case, this case, this case, this case, this case, not okay. Those two you have to do rotations. After doing the rotations, you will get only this. Now you see the what we are doing here, guys. Here, take the first case. Take the first case again. First case, this is what we are talking now. Which element insertion is making unbalanced? Which element insertion is making unbalanced in the case 1? Which element insertion is making unbalanced? 30. Wonderful. 30 is making. Which is becoming unbalanced, whose balance factor is 2, that is 10. And now where this 30 is inserted? 30 is inserted in right of right. Is it? Right? Right. So to correct this case 1, you need to go for, sorry, right means RR rotation is required. We'll talk about how to do rotation later. So because you are inserting right of right, you need a RR rotation. Is this clear? This is 1. Right you are inserting. Next, come to the case 2. Case 2, which element is causing unbalanced? 10 is causing unbalanced. So where 10 is inserted? It is a left of left, right? Left, left. So here we need left, left rotation. LL rotation. How to do it later, we'll do the next. First, identify the rotation types. We are inserting right, right. So because of 30, which is inserted in the right, right, this is becoming unbalanced. So I need RR rotation to make it balance. And here I am inserting 10, which is the right of right. That's what my tree becomes unbalanced. So I need LL rotation or left, left rotation to balance this particular tree. And take the case 3, guys. Case 3, where I am inserting C, which is causing unbalanced. In case 3, which element, which node is causing unbalanced? Which node is causing unbalanced, guys? Which node is causing unbalanced in case 3? Is that 20? 20 only, right? So how 20 inserted, tell me? 20 is causing and unbalance is the root. So how 20 is that? Is this right, left, right, left, right, left? So you need here, guys, RL rotation. RL rotation. Remember, these rotations are not only for AVL tree. These rotations also will be useful for red black trees also. Red black trees also same rotations. Rotations are common for BSTs. These are the common. But the way you calculate imbalanced may be different. The way you calculate, the way you find whether BST is unbalanced or not, in AVL tree, you're going to check with the balance factor. In maybe red black tree, you will check whether there are some other rules of red black combination. The rules are different. Once you identify it is unbalanced, in AVL tree, the way to identify unbalanced is different. In a red black tree, the way you identify the unbalanced is different. But once you identify the tree is unbalanced, the way of rotation is common in AVL tree and red black tree. The way of doing the rotations are common in both AVL tree and red black tree. Fine. The last one, guys. Last case, we have fourth case. Which element is causing unbalanced? This is 20 is causing. Now, how it is done? See, left, right. So we need here as L R rotation. LR rotation. So total how many types of rotations are there? Number one, LL rotation. Usually we'll start left, right. Second, RR rotation. These are simple rotations. Number three, LR rotation. Number four, RL rotation. How many rotations are there in AVL tree? 4 rotations. LL rotation, RR rotation, LR rotation, and RL rotation. 4 rotations we have in AVL trees. How many rotations in red black tree? Red black tree also same 4 rotations, guys. Red black tree also same 4 rotations. We'll see that anyway. Okay. We'll start exploring each one. First, we'll start LL rotation. So when we need LL rotation from this, we need the keys 30, 20, 10, right? Okay, go to the next page. First, we'll start with LL rotation. Indirectly, LL means left, right? LL means left. So what are the keys we have to consider here? Tell me. What are the keys we have to consider here? I think left means 30, 20, and 10. Okay, they are the keys. So now we are learning rotations with AVL trees. Remember it. Now we are learning rotations with AVL trees. Okay, guys. First insert 30. Insert 30. Yes, I am inserting 30. What is the balance factor of this? 0. So cool. Next, insert 20. Where I had inside 20 lesser. So come here. Now update the balance factor in the tree. So this is becoming 0, this is becoming 1. 0 allowed, 1 allowed. So this is a balanced. Done. Next, insert 30. 10 the smaller. Come here. Sorry, 10 it is. Update the balance factor. 0, 1. Whenever you find a 2, immediately you have to do rotations. So what rotation? We understand this. Left rotation. When you are doing a left rotation, rotate towards the right side. When you do LL rotation or left rotation, rotate towards the right side, guys. Rotate towards the right side. Only 3 nodes you have to touch. Don't touch any other nodes. Only 3 nodes you touch. 3 nodes you touch. Why 3 nodes only I am telling here is, even it may have other elements, but only 3 nodes you have to rotate. So from these 3 nodes, you can remember as a formula of this. 3 nodes you have. see, maybe I'll take a bigger tree. First understand the the basic idea. So you do the rotation, guys, here. After rotation, when you do like this, so this three I'm considering. The middle one, you make it as root. Middle one, you make it as root. So and 20, I'm making as root. 20, so 30 should come like this. You are shifting the like this means 30 comes this side. And 20 child remains as this. Now update the balance factor 0 and 0 and 0. So now my tree is balanced. My tree is balanced. Wait, I'll just make it a smaller. So do the rotation here. So 20 becomes the root and 30 comes this side, 10 comes this side. Update the balance factor 0, 0 and 0. So super cool, right? This is perfectly balanced. All zeros, perfectly balanced, right? Perfectly balanced binary search tree it is. LL rotation is clear? LL rotation happens. You need to do LL rotation when you are inserting the node left, which is causing the unbalanced. Then rotate towards the right side. When you're doing LL rotation, rotate towards the right side. Wonderful. Come to the another simplest. I'm taking RR rotation, guys. RR rotation. Right rotation. So the keys I'm taking here are 10, 20, 30. This only makes the RR rotation. Okay. First insert 10. Okay, done. When I insert 10, what is the balance factor of this? 0. Okay, no problem. Then 20, higher, come this side. Update the balance factor. This is 0, this is becomes 1. Next, insert 30, higher than 20. This comes here. Now update the balance factor immediately. 0, 1, 2. Oh, we got a 2. Whenever we got a 2, this becomes unbalanced, which is causing 30 is causing. How 30 is inserted? This is right. So we need a RR rotation. Remember this, guys. When you're doing RR rotation, shift towards the left side. Shift towards the left side. Shift towards the left side. So do the rotation. When you're doing like this 20 should become root and 10 becomes child and 30 remains here as this. This is perfectly balanced. Update the after that. If you see, yes, all are this done. Finally, you are getting same thing. See, 20 is the root, 10, 30. If I give 3 elements, 10, 20, 30, if you want to make it, only this is the option, right? Is this clear, guys? In LL rotation, you are shifting towards the right. In RR rotation, you are shifting towards the left so that your tree becomes balanced. Is this clear, guys? Okay. So we are done too. Next. Third case, LR rotation. I'm using LR rotation now. For LR means where you have to insert. When it is, you insert a left and then right. Left and right. So what data I have to take? I have to consider the data. The data is important. This is all becoming depending on the data only, right? So I'll take my keys for this as first 30 I'll take 30 on the top. Then I want a left means smaller I want. Its right means 20. This is my data. My data is coming like that. I can't do anything, right? If I get a 10, 20, 30, we see previous case. If I get data as first 30, 20, 10, that case is different. Now my user is giving data first 30. First I got a 30. Okay, inserted. Now it is cool, no problem. Next user is giving 10 for me. 10 I inserted. 10 comes to the left side. Okay, 10 inserted. Then user is giving 20. 20 I should give it as this side. So now whenever before inserting 20, no problem, right? This is no problem, guys, right? This is the 1 and 0 factor. So no problem. Whenever I'm inserting 20 here, when I update the balance factor, this is 0, this is 1, and this is 2. So becoming imbalanced. So this is unbalanced. Unbalancing is happening because of a left and right insertion. This LR rotation is a double rotation. Double rotation means you have to perform the rotation 2 times. So this you have to perform in 2 times. The first rotation, see carefully. You do the first rotation like this. It means this is the rotation 1 in this. Rotation 1 is, this means this 20, 10, these two, between these two only. You move like this. And if you see this, it becomes the previous style only. 30, 20 becomes the root, and 10 becomes the child. This is already we have seen, I think, previously, if you remember it, guys. Now do the rotation 2. Rotation 2, which side I have to do? Rotation 2, which side I have to do, guys? Now rotation 2, which side I have to do? Right, very good. Do the right side like this, like this. So this becomes now same, guys, 20, 30, and 10. So rotation 1, which side you are doing? Rotation 1, you are doing left side. Rotation 2, which side you are doing? You are doing right side. This you are doing exactly LR, first left side, then right side. LR, first right side, first left side, and second is right side. Is this clear about LR rotation? The double rotation. LR rotation is double, 2 times you have to do to make it balance. Clear, guys? I'm going for a 4th rotation called RL rotation. These all again a common for red black also. I won't explore there again. Same thing, anyway, you know that, right? Fine. So here the data is important. My user is giving first 10, guys. Then I want a right side insertion. 30 I want. Then I want to come for right, then left. Left means 20 I'll take. Okay. Do first 10. Yes. Then 30. Yes. Up to this, my tree is balanced. 20 less than 30. So make here 20. So now if you see the balance factor 0, 1, 2, immediately my 20, the current node I am inserting is causing unbalanced. So I have to do a rotation. Here the rotation I need is RL because this is happening with right and left insertion. So you tell me how to do 2 rotations, guys. Tell me which rotation first and then which rotation. Rotation 1, which side I have to do? Rotation 1, which side I have to do? Right side, right? So you do like this first, right side. So how it becomes now? How it becomes, tell me. First 10 is the root, was the child of this, 20 will come, child of this, 30 will come. It is still unbalanced. That's what left, this is right is over. Next, again another rotation is required. Rotation 2 is required here. This side, this should be left. Do like this. Do like this. And this where you are doing? Left side you're doing. You know this is already we have done it. Now you get a 20, a 10, and then 30. So we have perfectly balanced Bannister's tree whose height remains the minimum so that we can do all the operations on this AVL tree, a balanced, self-balanced tree with a log n time complex tree. So all 4 cases clear, guys. Remember, always rotations happens on a 3 nodes only. I'll tell you now we are considered example 3. You can say I've taken a 10, 20, 30, 3 only changing always. Even when you have 100 elements also, rotations happen 3 nodes. One important point. I'll show you that practically later. Next, means we look always in 3 nodes. I just these 4 cases remember as a formula. Always you look at the 3 nodes. How to rotate 3 nodes you consider enough. Remaining makes as it is. And already I told you, whenever a balance factor becomes 2, immediately do the rotation. Which rotation? Depending on the case. If the insertion happening on the left, do LR rotation. And if insertion happening on the right, do RR rotation or LR rotation or RL rotation, depending on the case you are implementing. Is that clear, guys? Is that clear about the rotations? So we just considered 3 elements. You can ask, you considered only 3 elements. Now how it works, we'll see that. We'll take a small break now. After the break, we'll do more examples, more use cases. We'll take a big tree and how to do these rotations on that. We'll understand after the small break. So AVL trees will be continued in the next session.